Hey guys, Ishan here. Hopefully you've watched my last video on cardinality because that deals with finite sets. But now we're going to discuss uh, infinite sets. And yeah, let's get down to it. Let me share my screen, start this broadcast. And you should be able to see my screen. So as the name kind of implies, an infinite set is a set with infinitely many elements. And you can kind of think of it as a box, like I said in the last video, but this time you have infinitely many items. I like to think of cats. So say I have a box with infinitely many cats. It doesn't really make sense, and it kind of breaks down our it kind of breaks down our mental model, but that's okay. It's cute, and we'll just go with it. So what are there are two different kinds of countably infinites or of infinite sets, countably infinite and uncountably infinite. So as we've said already, both have infinitely many elements, but why don't we try being able to differentiate them a bit better? So we can say that if we want to just speak formally, that with the countably infinite sets, you can draw a one-to-one relationship with the elements in that set and the natural numbers. Uh, sure, I guess. That doesn't really make sense. So I'm going to tell you what I use to just quickly determine, like a quick heuristic to determine, is this thing even countable or is it uncountable? So once I've identified that a set has infinitely many elements, I want to see, is it possible for me to count and start counting and eventually reach all of these elements? And the best way to look at that is probably through the natural numbers. So we already know that the natural numbers is countably infinite because of course it has a one-to-one relationship with itself. But just as a thought experiment, is it possible to start counting the natural numbers and given infinite time reach every natural number? Well, yeah, you could say, let's start at 0, then 1, then 2, then 3, then 4. And if I just kept on counting and assuming I'm immortal, so I have infinite time, I could theoretically reach all of the natural numbers. Now, don't get me wrong, I kind of have a life, so I don't want to sit here and do that, but it's possible. Now, let's look at some other sets and let's determine whether or not they're countably infinite. So another set we could say is Z plus, the positive integers. And the positive integers, as the name implies, goes from 1, 2, 3, 4, and it has infinitely many integers. So can I count that? Yeah, I could say 1, then 2, then 3, then 4, and just keep on going. Again, I have a life, so we're not gonna keep on going. Now, what about the integers in general? Let's see. So this is kind of harder because you have two directions and it stretches both ways, both directions, infinitely forward in both directions. Like you have positive infinity and then negative infinity. But I still want to know, is it possible to count this? And so I'm going to actually say yes. We could say 0, 1, then -1 to make sure that we're accounting for both sides. And then just keep on progressing further. 2, -2, 3, -3. And eventually I'd reach all of the, eventually I would reach all of the numbers in a set of integers. You might think, well, wouldn't it take me twice as long as the positive integers? Well, yes, but twice times 2 times infinity is still infinity, so it doesn't really make much of a difference. Yeah, and then we could say dot 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 infinity, negative infinity. We discussed the rational numbers in lecture, and I don't want to dive too deep into that, but remember, if you do like diagonalization, you can count all of the rational numbers. And now I have one more set that I want to talk about. Z plus time cross Z plus. This is essentially the set of ordered pairs with positive integers. So like 1, 1, 1, 2, 2, 1, and then like 69, 420. Where did those numbers come from? I don't know. But yeah, the question is it possible to count all of these numbers? And you might be thinking, okay, so one way might be to say it has, if we can do a cross product, if we look here and say infinitely countable times infinitely countable, is that still infinitely countably infinite? And the answer is yeah, we can definitely count this. And again, we can do this kind of diagonalizationally, but we're not going to dive deep into the formal proof of that. And essentially, you want to start with 1, 1, then go to 1, 2, 2, 1. Then you could do 1, 3, 2, 2. I'll just write this down. 1, 3, 2, 2, 3, 1. And you'll start to realize that there is indeed a pattern, and you can and you can definitely count all of these numbers. So now I have a challenge question for you. So for the Z, is it possible to do Z plus times Z plus, wait 1 second. Uh, so sorry about that, guys, but we are going to get back to it. So Z plus times Z plus times Z plus, and let's say we have infinitely many, let's say we have infinitely many of these numbers, the positive integers. So is it possible to count all of them? And honestly, I'm going to say no, because what we did in the previous example is that we said that uh, essentially what we did is that we combined terms that had the same sum overall. And you could see that this has a sum of 2, this has a sum of 3, and then we went to ordered pairs with the sum of 4, and we went on like that. But in this case, when you have infinitely many positive integers, then there's no way that you can possibly compute a sum. And the, yeah, so it's unfortunate, but this is going to be uncountably infinite. Let's take a look. One way I like to think about this is by saying that uncountably infinite is equal to countably infinite to the countably infinite power. We don't need those. To the countably infinite power. I wrote that wrong. Okay, so apologies for my bad handwriting, but uncountably infinite is equal to countably infinite to the countably infinite power. And if that makes sense to you, then great. But if not, don't worry about it. Yeah. Now let's look at a few more sets. So the real numbers, as you probably remember, those are not going to be countable because you just don't know where to start. Maybe you could say, oh, I'll start at 0. But how are you going to reach every possible real number? There's just no way that you can count them all. The same thing goes with the sets 0, 1 inclusive, or even 0, 1 exclusive. Sure, you could say that I'm going to start at 0, but your second number in the sequence, how many zeros is it going to have before your first one? And no matter what number you give me, I guarantee you I can always find a smaller number than that. So I think there's one last set that I want to show you, just so we're not confused. And that's going to be the set containing the natural numbers. So I want you to think to yourself for just 15-20 seconds. Is this set countably infinite or uncountably infinite? Okay, now that you're back, let's go back to our box analogy. Remember that this set of natural numbers, or n, is a set in itself. So if we could write this out as the set of 1 or 0, 1, 2, ... infinity. And we have a big box. Let's draw that. And then a smaller box inside of it. Now, do we care what is inside the smaller box? No. So the answer to this question, what is the cardinality of this set, which is the set containing the set of natural numbers, it's actually just 1. And it's neither countably infinite nor uncountably infinite. It's just finite. And so hope you enjoyed that last little brain teaser. Yeah, if you guys have any questions, feel free to ask on Piazza. But bye.